Welcome to G Fun Facts Online. Today, we're journeying to a place of immense power, a scar left by a cosmic hammer blow. But we're not traveling to space. We're diving deep beneath the frigid, dark waters of the Barents Sea, off the northern coast of Norway. Buried under hundreds of meters of sediment, there lies a secret from the age of dinosaurs. It's a colossal impact crater, 40 kilometers across, named Mjolnir, after the mythical hammer of the Norse god of thunder, Thor. For 142 million years, it lay hidden, a ghost on the seafloor, until modern science gave us the eyes to see a day when the heavens fell. The story of its discovery doesn't begin with a colossal bang, but with a series of quiet, squiggly lines on a computer screen. In the early 1990s, geologists were doing what they often do in the Barents Sea, searching for oil and gas. They were using a technique called seismic reflection. This is essentially a geological ultrasound, where you send sound waves down into the Earth's crust and listen for the echoes that bounce back. By analyzing these echoes, you can map out the different layers of rock beneath the seabed. As they processed the data, a strange and enormous pattern began to emerge. It was a huge, semicircular structure of heavily disturbed rock. It was massive, about 25 miles in diameter. A geologist named St. Gudlaugsson first described it in 1993, and he put forward a bold hypothesis. This wasn't just a weird geological formation, it was the scar from a cosmic impact. Now, proposing an impact crater is one thing, but proving it is another, especially when it's buried deep under the ocean. On Earth, evidence of impacts gets erased. Our planet is geologically active. Erosion wears craters down, sediments fill them up, and plate tectonics can literally swallow the land they're on. An undersea crater is even more elusive. The ocean floor is constantly being recycled, and surveying the deep ocean is incredibly difficult and expensive. For a while, the Mjolnir structure was a fascinating but unproven candidate. The seismic data was compelling, showing a classic complex crater shape, an inverted sombrero, with a prominent central peak where the crust rebounded after the impact. But scientists needed physical proof. They needed a smoking gun. The breakthrough came from a borehole, a deep hole drilled into the seabed. Crucially, this borehole wasn't even inside the crater itself, but about 30 kilometers from its edge. Scientists retrieved a long cylinder of rock, a core sample representing millions of years of geological history. As they analyzed this core, they found it. Within a specific 0.8 meter thick layer of sediment, they found two definitive pieces of evidence. The first was shocked quartz. When a massive object hits the Earth at hypervelocity, we're talking many kilometers per second, it generates pressures so extreme they are almost unimaginable. These pressures are far greater than anything produced by normal geological processes like volcanic eruptions or earthquakes. This extreme pressure sends a shock wave through the rock that physically alters the crystalline structure of minerals like quartz, creating a distinctive pattern of microscopic fractures. Finding shocked quartz is the gold standard for confirming an impact. But there was more. In that same layer, they found a significant spike in the element iridium. Iridium is what's known as a siderophile, or iron-loving element. During Earth's formation, most of our planet's native iridium sank with the iron to the core. As a result, it's extremely rare in the Earth's crust. But where is it common? In asteroids and comets. Finding an iridium-rich layer alongside shocked quartz, both dating to the same period, was undeniable proof. The giant, buried structure was the Mjolnir impact crater. With the what confirmed, scientists could begin to piece together the when and how. The evidence pointed to a single, cataclysmic day approximately 142 million years ago. This was the early Cretaceous period, at the boundary between the Volgan and Ryazanian ages. Dinosaurs roamed the land, and the world looked very different. The Barents Sea wasn't the deep, icy expanse it is today. It was a shallow marine shelf, with water depths estimated to be between 300 and 400 meters. Let's paint a picture of that day. A massive object, an asteroid or comet, estimated to be about 2 kilometers, or 1.2 miles wide, came blazing through the atmosphere. It struck the shallow sea with a force that defies comprehension, equivalent to the explosion of millions of nuclear bombs. The impact was so powerful it didn't just splash the water away. It instantly vaporized a huge volume of the sea and the seabed itself. It penetrated deep into the Earth's crust, creating a transient cavity that was at least 4.5 kilometers deep. This initial deep bowl was unstable. In the seconds and minutes that followed, the sides collapsed inward, and the rock at the very center, which had been compressed downwards, rebounded upwards with incredible force. This rebound formed the prominent central peak that we can still see in the seismic data today, a mountain rising 250 meters from the crater floor. The immediate aftermath would have been nothing short of apocalyptic for the region. The impact in the shallow sea triggered a colossal tsunami. We're not talking about the tsunamis we see in the modern day. We're talking about a mega-tsunami, with waves that were potentially hundreds of meters high. These waves would have radiated outwards from the impact site at the speed of a jet airliner. In 2006, geologists studying ancient coastlines in southern Sweden found evidence of a massive, anomalous flood that occurred right around 145 million years ago. The timing is so close that it's now widely speculated that this was the destructive signature of the Mjolnir tsunami, which would have inundated coastlines for hundreds if not thousands of miles around. But the destruction didn't stop with the waves. The impact struck a region that was geologically rich in organic sedimentary rocks. These are rocks that contain ancient organic matter, the raw ingredients for oil and gas. The intense, searing heat of the impact likely ignited these hydrocarbon-rich materials. This would have released enormous quantities of soot and other aerosols into the atmosphere. In fact, rock samples associated with the impact layer show traces of this soot. This plume of debris, combined with the vast amount of water vaporized and thrown into the sky, could have had a significant, if short-term, effect on the regional climate, blocking out sunlight and causing a sudden, sharp cooling. The naming of the crater, Mjolnir, is a perfect tribute to the sheer scale of this event. In Norse mythology, Mjolnir is the hammer of Thor, the god of thunder. It was forged by dwarves and was said to be a weapon of terrifying power, capable of shattering mountains with a single blow. The name itself is thought to mean crusher or grinder. Naming this geological feature after a mythical weapon that falls from the sky and crushes the earth captures the essence of the event perfectly. It's a modern scientific myth grounded in the hard reality of geology and physics. The Mjolnir crater is one of only about 200 confirmed impact structures on Earth, but it holds a very special place among them. It is one of the best preserved submarine impact craters ever discovered. This gives scientists a unique natural laboratory to study something called a wet impact. Most of the craters we can easily study are on dry land. But Earth's surface is over 70% water, so statistically, most impacts throughout history must have happened in the ocean. The presence of a water layer, even a relatively shallow one, dramatically changes the physics of a crater's formation, how the energy is distributed, and where the ejected material ends up. Mjolnir provides a crucial data point for understanding this common but poorly documented type of event. It helps us refine our models for what would happen if an asteroid were to strike one of our oceans today. While Mjolnir is smaller than the true giants of Earth's impact history, like the 300-kilometer Vredefort crater in South Africa or the 180-kilometer Chicxulub crater in Mexico, famous for its role in the extinction of the dinosaurs, it was still a globally significant event. Its discovery and study help us understand the frequency of these large impacts and the hazards they pose to life on Earth. And in a fascinating twist, this story of ancient destruction has a surprisingly modern relevance. The same seismic surveys that led to the crater's discovery were looking for oil and gas, and the crater itself has become a point of interest. The immense force of the impact heavily fractured the rock in and around the crater. This fracturing, combined with the region's existing geology, created a network of cracks and voids. These structures are ideal for acting as geological traps, where migrating oil and gas can accumulate and get stuck. In fact, seismic data suggests that the southern part of the Mjolnir crater has high hydrocarbon potential, with anomalies that could indicate trapped reserves. It's an incredible irony. A cataclysmic event from 142 million years ago might now hold a key to powering our 21st century civilization. The Mjolnir crater is a profound reminder of our planet's dynamic and often violent history. It teaches us that even the most remote, placid-seeming parts of our world can hide evidence of unimaginable power. For millions of years, the giant slept in its watery grave, a silent testament to a time when a cosmic hammer truly fell from the sky, crushing the Earth and reshaping a corner of our world forever. Its discovery is a triumph of scientific curiosity, a story that not only illuminates our deep past, but also helps us better understand the present and prepare for the future, reminding us that the sky above is not always silent,